Presentation is Jemma Bennett from the University of Durham. We'll be talking about using copies to improve precision in continuous time quantum computation. Over to you, Jemma.
Hi, thank you very much for inviting me to talk. And today I'm going to talk to you about a technique that we've developed that uses copies in order to improve precision in continuous time quantum computing. And the first thing to mention is that if I do a bad job of explaining it today, or you just want more details, then there is a paper available on the archive at this link here for extra details. Okay, so I'm going to tell you about how our technique for improving precision works today. But first, before I tell you how it works, I need to tell you why we need to improve precision for continuous time quantum computing. So, as theorists, we want to solve optimization problems on our quantum computers, and these come in all sorts of shapes and sizes. But the main thing about these problems is that the solution is the lowest energy state of these particular problems. We like to represent our optimization problems on Ising models. Here is a very simplistic Ising model. Yeah, you can see my pointer, that's good. Just 2 qubits. Each of these qubits have a field applied to them, H0 and H1, and it's connected by a coupling strength J01. If we want to know about the energy levels of this Ising model, then we can look at its Hamiltonian, which will look something like this. So if we want to represent an optimization problem on this Ising model, the thing is, as we want to represent more and more complicated optimization problems, we increase the number of terms that we need in our Ising model, and also the fields and couplings that we want to have on our Ising model become more and more complicated. So you could end up with fields that look more like this. And this, unfortunately, is where reality may have to step in, because when we try and set our optimization problem on a real-life quantum computer, we become limited by the fields and couplings that we're able to set on our quantum computer, such that if we're trying to represent this more complicated number here, what we may actually end up setting is something more like this. And the problem with that is that you're shifting around the energy levels in your Hamiltonian, such that when you come and find the ground state, or the answer to your optimization problem, you end up finding completely the wrong answer than the one that you were looking for. So how do we go about stopping finding the wrong answer? Well, a naive approach might be that if you try and find the ground state the first time and get the wrong answer, you could just simply try again, and you might be lucky the second time and get the right answer. But we actually want to do better than this. So building on and making several differences to a technique called QAC, we start off by connecting several copies of an Ising model together. We then subject each of these Ising model copies to a lack of resolution. So a lack of resolution on the fields and the couplings in our Ising model. And we define this lack of resolution as a number of allowed values between -1 and +1, which itself is defined by 2 to the p + 1, where p is the precision. And we vary this p from 1 to 10. So here's an example here where we have low precision, and you see there's a low number of values between -1 and +1 that we're able to set. So this means that the problem that we're able to set on our quantum computer is not going to be very close to the one that we want to set for our optimization problem. But as you can see, as we increase the precision, there are more allowed values between -1 and +1, and this means that we are getting closer to, so we're able to set our H's and J's closer to the ideal values that we need for our optimization problem. We then measure, once we have subjected our Ising model copies to a lack of resolution, we then measure something we define as fraction correct. That is, once subjected to a lack of precision, the fraction of times we still find the correct ground state of our Ising model. A key subtlety to our technique is that we only require one or more of these Ising models to have the correct ground state for us to consider this run a success. We then have tested our models on several different examples. So here we have 2 or 3 copies of spin glasses and spin chains. And what we wanted to find is what is the optimal strength of links between copies that we needed in order to maximize the fraction correct. And what we find is this. So here we have our different examples again, 2 copies and 3 copies, and what we've measured is fraction correct versus the strength of the couplings between the copies. And here we see that we have varied the inter-copy couplings between -1 and +1. So here are ferromagnetic links and here are anti-ferromagnetic links. And the 2 colours represent a p equals 3 and a p equals 4, so a lower precision and a higher precision. And these dotted vertical lines are representing the allowed values between -1 and +1 that we are able to set for our couplings between the copies. And what we see is that in these cases, that there's an optimal value of JF where the fraction correct is maximized. So this is the ideal strength of coupling that we want to set in between our copies. Another interesting thing to note is that for 2 copies, we do have this maximum in fraction correct, but the improvement tails off quite quickly as you increase the strength of your antiferromagnetic links. On the other hand, for 3 copies, we don't see this tail off as much. So this...
What was the yellow and the blue data?
So the yellow data is for p equals 4 and the blue data is for p equals 3. So you might just be able to see, the yellow is probably not very clear in this, but the sort of vertical dotted lines represent the allowed values of yellow, and then the blue ones correspond to the allowed values of p equals 3. Okay. So what we've seen there is that 3 copies is better than 2 copies. So we want to know why is that, but also we want to know why does it work in the first place. And the answer to that question is energy penalties. And so what we have here, instead of just having a single optimization problem, it's 2 optimization problems connected together, but anti-ferromagnetically. So the optimization problem wants to be in its preferred ground state, but the links in between them are working against them. So you see that if we have 2 copies that are exactly the same, then this receives the highest energy penalty. The more states we flip compared to the original copy, the lower this energy penalty becomes, until we see that if we have a completely flipped ground state compared to the first ground state of copy A, then we see that we actually receive the largest energy benefit from being in this situation. But it's more likely that this state is going to have a much higher energy because it's not the optimal state for your optimization problem. Another way of looking at this is something like this. And what I've plotted here is the energy levels versus the possible states of our 5-qubit Ising model. So a little bit confusingly, I admit that I've changed out the 5-qubit bit strings to decimal numbers, but don't worry too much about that because I'll just explain it now. So what I've drawn here is the energy levels for a p equals 3 problem. And what we can see by these dots is that, so in this orange dot here is the ground state of the original problem with true precision. And what we see is that this is actually higher than this dot here, which is the ground state at p equals 3, which means that this example is broken by the lack of precision. And I've drawn in some arrows here. And what these arrows represent is the energy boost or downshift, which is given by connecting the initial copy with the second copy of, together. So if we look at the ground state here, we see that there's a large energy penalty or boost, because this is what representing what would be the case if I just connect 2 copies of the same, two of the same copies together. On the other hand, we see that if we connect a completely flipped copy to the original copy, we see that it has a large downshift, but this is nowhere near enough to overtake the two copies that are the same. So this is also not optimal. But what we do see is that there is another low-lying state which is almost completely flipped, but is low enough that it overtakes this incorrect ground state and connects with the true ground state rather than the incorrect ground state. So, sorry, that explanation may have been a little bit confusing, but what I'm trying to say is that, so we started off with the original ground state when there was no errors subjected to it. By subjecting a lack of resolution, we then had this shifted to a different ground state, so it was broken. And then by connecting these two copies together, we're able to recover the true ground state along with almost fully flipped connector state, because this just, so you can think of it as, now we're not just trying to solve the optimization problem, but kind of coming to a compromise between the optimization problem and the anti-ferromagnetic, satisfying the anti-ferromagnetic links, which is what we think is providing us this improvement from connecting these copies together. So now we thought about two copies connected together. Why is 3 copies better than 2 copies? Well, at first you might think, well, there's 3 copies, so there's going to be a larger energy penalty to having them all in the same ground state. Well, this is true. But what we see is that when we flip a bit compared to of one of the other states, we see that this energy penalty reduces. But then when we flip another bit, the energy penalty stays the same. So for the anti-ferromagnetic links, these two different ground states are energetically kind of not preferred. And we find that, in fact, if we connect all 3 copies together, we only get an energy benefit of -5, so not as strong as the energy penalty you can get by connecting all 3 of the same together. But the interesting part is that the frustrated link that you need in 3 copies, it does not necessarily have to be in the same place between all these 3 copies. So in order to maximize the energy benefit, you do not have to have a completely flipped antiferromagnetic state. So it's almost more likely to be a state that is closer to the correct ground state. And this is why we think we do not see the tail off as strongly for the 3 connected copies. Okay, now I've tried to explain a bit about behind why it works. I'll go on to some more concrete results that we've got. So what we decided to test is Ising spin glasses, because they're NP hard and also uniformly hard, and they've been studied in the continuous time setting in this paper here. And we connected 3 of these copies together in this loop or triangular configuration. And we also set these links to be optimal, so the minimum allowed antiferromagnetic links, as seen in this graph here. And then we measured the fraction correct, remembering that we only need more of these copies to be correct for us to consider it a success. We then measured this against the fraction correct of just having single copies on their own, and for different values of p, so the p going from 1 to 10. We could also measure a breakdown of the fraction correct, so fraction of the time there are 3 copies correct, 2 copies correct, or just 1 copy correct. And then we could plot this versus the precision. And on the left-hand bars, you see the results from a single copy. So you can see that as the precision increases, the fraction correct also increases. This is what we would expect. As the precision is increasing, we're getting closer to the optimization problem that we'd ideally want to represent. But interestingly for us, these right-hand bars are the results from 3 connected copies. And what we see is that there is an improvement or an increase in fraction correct from just a single copy to 3 connected copies. And interestingly, this is not caused by just having 3 copies correct, but by having 2 or just 1 copy correct out of the 3. we also wanted to measure the effect that our technique had on instances by themselves. So the fraction of times our technique had no effect on the ground state, the fraction of times it had a positive effect, so we recovered the ground state from a broken instance, and then the fraction of times it had a negative effect, so the fraction of times an instance's ground state was broken by using our technique. And what we found is that for the majority of instances that it doesn't have any effect, but positively for us, there is this bar, small bar here, that indicates that there is a proportion of instances that are corrected by using this technique. And also good for us, there is only a very small situation where instances are broken by using this technique. And if you really wanted to get this tiny improvement from using that we lose from using the free connected copies, you could ideally have an external individual copy on its own, such that you could account for when this was happening. So if you can see that these are examples, these are just examples from 5 copies, and if I just replace the graph to look like this is the same graph, but instead with lines and dots, and the solid line is for the free copies and the dotted, other way, is it the other way? Yeah, the other way around, yeah. Solid lines for single copies and dotted line is for the free connected copies. And so we repeated this for 5, 7, 8 and 9 qubit spin glasses, and the gap between the solid line and the dotted line indicates that the improvement continues for larger sizes, which is good for us. And we also wanted to measure the gain in bits of precision that we were getting, or the relative gain in bits of precision that we were getting from using just a single copy between using just a single copy to using 3 copies. So what we did is we instead flipped the graph around to measure the fraction incorrect, and plotted an exponential fit to the single copies, and then used the measured horizontally from the 3 copies, the fraction incorrect for the 3 copies, to measure the relative increase in precision we were gaining from using 3 copies. And what we found is a graph like this, which indicates that as precision increases, precision improvement increases a little bit, and we find that around p equals 7, we're getting roughly 3 bits of improvement. We also wanted to check how, so up until now we've just been looking at instantaneous ground state, so just finding the ground state classically, but we also, and this could be seen as the same as just doing a perfect like adiabatic evolution to find the ground state. But what we wanted to see is whether this works with other types of continuous time techniques. So we chose quantum walks, and the key thing about these is that you don't necessarily get the answer with probability 1, and that it accesses excited states along the way to finding the ground state. And so it looks something like this. So here we have the target or problem Hamiltonian. It's just our spin glasses that we had before. And we have the driver Hamiltonian, which looks like this. And a key thing that we wanted to check was gamma, because for quantum walks there is an optimal gamma where the success probability is maximized. And these were previously found in this paper here. And we wanted to, for just single copies, we wanted to check the effect that our technique was having on these optimal gammas, because if this changed a lot, it could potentially indicate that our technique was having a negative effect on the success probability of the quantum walk. And so yes, so then we wanted to compare the single copies with true precision, single copies with precision equals 3, so an error added to them, and then the free connected copies with the lack of precision as well. And we tested this for 4 instances, just to get an idea of what was happening. And what we found is this. And so the green lines represent the single copy true precision, orange lines single copies with p equals 3, and then the blue line is the free connected copies with p equals 3. And what you see is various things are happening, but that's okay, because actually this is an average effect. But the key thing to us is that the optimal gamma does not seem to change much, so that we would be able to use a similar gamma when we were using quantum walks. Okay, and that's all I have for now. In conclusion, what we found that by connecting 3 copies with minimum strength anti-ferromagnetic links makes our problem more robust to a lack of precision. And this could be used to increase the effective precision of the optimization problem. And if you want more information, there's the link to the paper again. And thank you all. Also, thank you for my collaborators, and also thank you all for listening. And yeah.
Okay, we have time for questions. Let me grab the mic. Hello.
Do you know how robust is your system for lack of precision in JF?
So at the moment what we've done is just the JF that is, so JF was subjected to precision, but only the same precision as the rest of the copies. So, which, yeah, if you're, it kind of makes sense, because that's almost, if you're setting it at like the minimum precision that's available. So.
Yeah, also this is kind of related in the sense that if you increase the length of your chain and you have some not necessarily precise setup, then you can have different JFs on different links of the chain. And like, how does this affect the setup?
I am not sure about that, because yes. So yes. So we have only tested the links being the same. So we don't necessarily know as much. But yes, you could expect that potentially if you're just connecting 2 copies together, it would be quite sensitive to changes in the JFs. Also, there's kind of, it seems like in some situations it's better to leave, because this is an average effect, in some situations it's better to leave copies disconnected, or even certain qubits disconnected. And that seems to give a better success probability, but it's hard to know without solving the problem completely, it's hard to know when you should connect the copies or leave them disconnected. So that's an open question still.
Okay, thanks.
Well, there's a little bit more you can say from that graph, because the width of the...
Viv, do you want to take the mic?
Sorry.
Cheers.
The width of the peak, or if you look at that graph, the orange and the blue, the width of the peak it's not a sharp peak, so it's not only that minimum JF does it. You've got a little bit of leeway there. So can you see what I mean on the graph? It's not super sensitive to being exactly the minimum precision. You could, if it was twice that, you'd still have a pretty good effect.
Yeah, but this is still for the same value over entire chain. Yeah, and you could have like one part slightly on the right, the other part slightly on the left, and this doesn't mean that it averages to the same precision. Like I understand that this is like an open problem that you haven't investigated, but it'd be nice also to see.
Yeah, well, you're talking about having very different available precisions in the setting in the hardware. I'm not quite sure where the difference is coming from.
Like, from, let's say, hardware perspective, we can assume that we will never have infinite precision, yeah? So setting up all JFs equal to a given value is impossible, and some sort of fluctuations will be present there, and one fluctuation can drive us to the plus, the other to the negative side, and like, here you assume
Oh,
that
I see. You just,
everything is
well,
the same.
Jemma didn't go into this for time, but to avoid degeneracy in the small samples that we're using, we actually did put fluctuations on all of the values. So we have, I think, essentially tested what you've done, because if you try to do it exactly, your results get very skewed by degenerate ground states. So I think for practical numerical reasons, we have in fact covered what you're asking. But yeah, that was going to be confusing to explain that on top of everything else.
Ah, Glenn. Going in the wrong direction, sorry.
Okay, thank you for the talk. And I was wondering, like, these precision errors that you discuss are precision errors on the final Hamiltonian, just on this, how you're setting the parameter.
Yes, it's like the target, the precision
On
error
the
is
target Hamiltonian, on the
yeah.
target Hamiltonian. Because like in the Grover problem, I think Itai Hen and the collaborators, they checked that these precision errors indeed like wash out the Grover speed up, but they also looked at these errors which were just on the schedule, not necessarily just on the final, but like a perturbation of the schedule. Would your approach help also for these kind of errors or not? Or do you have to change it? Or is it just for the error on the final, on the target Hamiltonian?
So that's what we checked. We haven't done any errors on like the driver Hamiltonian, if that's what you mean.
Yeah.
So we haven't done that. We just put errors on the target Hamiltonian.
Okay, I see.
Sagato, is this a question? It's a question for Sagato.
So very interesting work. Yeah. So I was just wondering, in this same picture here, so you told these frustrations help you in the 3 case, but what if you took unfrustrated, like you took 3 copies, but couple like nearest neighbors? What happens? So see if the 3rd copy was just below, right, without a frustration.
Oh, okay. So this is, I've done this, and it's similar to what happens with the 2 copies.
I see. And another question is that do you, when you couple copies, you're kind of making the energy more, the energy more lower of the 3 copies. So do you have to kind of fight it with like a more gamma, or does the time to reach the optimal also increase? When
Not that I have seen, like not really done cumulative effects of the quantum walks. Yeah, just looking at individual instances. So the gamma looked similar.
Similar. Okay.
Yeah.
Okay. Thank you. Mm-hmm.
Dennis.
Thanks. Could you go to the I think it was a slide at the very end where you showed the performance with quantum walks for the 3 connected copies? So right. So what I would typically expect is something like in panel B, right, where the it becomes worth if you have the precision 3, and it becomes a bit better again if you have then the connected copies. But on the left it's like worse, right? So you said it's an average effect. What does it mean in this context?
So even in instantaneous time, we find that although it is a small effect, that in some cases by connecting the 3 copies together, we lose the ground state. So the ground state becomes no longer correct. So that's what I was referring to by we only see an improvement when we take the average of all of the instances. So yes.
There's another effect, which
With quantum walks as well is slightly different. Yeah.
Somehow I always end up with a project that looks conceptually simple to describe what you're doing, and then the subtleties turn into 20 pages. Sagato knows all about this. It was true for this paper. But so if you just think adiabatic, you're only thinking about the ground state, right? And that's the probability for that state is the only thing you need to worry about. When you run a quantum walk and you measure, most of the time you'll measure an excited state because it populates many different states. So now your criterion for success is different. It's what's the probability of measuring a copy with a correct ground state, including the incited state probabilities, so that actually everything has changed in terms of the probabilities you're summing here compared to what you would do for the adiabatic case. So that we're still looking into, but I mean, this we just honestly said like all possible combinations can occur, but statistically it's a little trickier to look up both how it changes, because excited states are now valuable, they're irrelevant for adiabatic, and then to work out where they're valuable, because in any case those excited states also help you with the single copies, and at some level, right, you have a good reason, some probability of measuring the right answer even when you've broken the ground state. So that's the subtlety there, that it takes a lot more working out that we haven't done completely at this point. And but we're interested in it to know how quantum walks are working to solve problems. There's a lot of stuff behind that. So, yeah.
Okay, any more questions for Jemma? If not, let's thank Jemma again. Very nice talk. Thank you.